This is Ming-Yao from Ozen Engineering. In this video, this is a continuation of my series on firearm simulation. And in this video, I'll be showing you how to model bullet loading and clip kind of motion analysis using Ansys Ls-Dyna, which is one of our explicit dynamics tools. There are a number of ways to model parts that move around, and obviously in a assembly like a firearms assembly, because there are so many components sliding against each other, it's very much necessary to model the motion of various parts. This is a workbench project interface. I have a number of tools here modeling the motion of different components, including Ansys Explicit Dynamics, Ansys Ls-Dyna. These are two explicit dynamics tools. We also have two rigid body dynamics tools, rigid dynamics as well as Ansys Motion. We also have transient structural analysis. So all of these tools can model motion of various components. However, there are some benefits and drawbacks to each one of these. So I'll be going into Ansys Ls-Dyna as an example of using an explicit dynamics simulation tool to model the motion of different components. The big benefit of using explicit dynamics is its ability to capture arbitrary contacts. You don't have to predefine any contacts or connections. There is the ability to create a body interaction that automatically handles all of the contacts and connections in an assembly. However, this also leads to some unique challenges because unexpected or unforeseen contacts can occur depending on the size and quality of the mesh. So sometimes that is necessary to take into account of. Okay, it's saying it took me a little bit longer to get the license for this analysis because I'm testing out the new Ansys cloud licensing system as well. Okay, just like before, this is the assembly that we're working with. It's a half symmetry assembly of a gun. And with Ansys, we can go from top to bottom, and I'll try to replicate some of the things I did here. So one of the nice part about Ansys is that we have a huge library of materials for analysis. So if I look at steel, there's various types of carbon steel, low alloy as well as high alloy steel. So there's also annealed and hardened steel. So this makes it very easy to run simulations in Ansys. If I go back to our database here and look at, for example, hardened steel. There we go. So here are all the hardened steel. If I look at, for example, 4140, it has a plasticity curve, a temperature-dependent thermal expansion coefficient, as well as multiple SN curves for fatigue calculations. Temperature-dependent thermal conductivity, as well as specific heat is also included. So you can include any and all of these materials in a simulation quite easily. Next, we want to look at the parts, and we have a few parts here that don't need to be included in the simulation. Those little components that I didn't really care about over here, we can just go ahead and suppress these bodies, and now they've taken it out of the analysis. The part where explicit dynamics really shines is in the contacts, and namely there's this option to do body interaction where all bodies can interact with all other bodies, and self-contact is included, and they're treated as frictionless. So automatically I can have any of the components touch anything else without having to predefine it. So as this bullet travels up the path, bumping into various components, I don't have to explicitly define each component and predefine the contacts. Ansys Ls-Dyna will just find those contacts for me. We also have a set of contacts up here. These are predefined contacts, and we can choose to rename them based on definition. So the only one that I care about here is this contact here. Normally there are various mechanisms that'll pull back, and there's a pin that causes this component to rotate. Because I'm doing a half symmetry model, it's not necessarily, I didn't include all of the additional components in here. So I'll leave this as a bonded contact, and automatically this will set up the contact so that the components don't move with respect to each other. There is this maximum offset value. You want this to be, the default is very small, so if there's even a tiny amount of gap between it, it won't be connected. So making this a larger value helps to define it. The rest of this I can suppress, which means I'm not interested in including in my simulation, so selecting all of these and suppressing it. And that's all I really need to do for this model to set up the contacts. I have one bonded contact where as I move the slide here, it will pull back the other piece, the bolt. And then the body interaction is contacts automatically defined here. Go ahead and generate a quick mesh here. It's because of the complexity of the geometry, this will be a TET mesh, but that's okay for demonstration purposes. And we can always refine it to something more accurate later on if needed. Okay, so this is the mesh that Ansys created for me. You can see it's a fairly uniform TET mesh automatically, and this is ready to go for analysis purposes. However, because this is a demonstration, let's take a look at the mesh. This is about 100,000 nodes and 500,000 elements, so it's not too bad. But I'm running this on a laptop, so I want this to be a fairly quick analysis. So I'm going to increase the size of the mesh globally to a size of 5, and then I'm going to make the bullets a little bit more refined. So these will have a sizing of 2. So I'm deliberately getting a lower quality result so that I can get results quickly. So much coarser mesh, but now this is only a few thousand elements, so it'll run very quickly. So it looks like some of the elements didn't get meshed. Oh, because I didn't suppress this one. I missed the one of the elements. So these little check marks tells me which one's meshed and which one hasn't. So now everything has been meshed. So let's go ahead and set up this simulation now. This is an analysis, and we'll set an in time to 1.5 e to the minus 2, so 15 milliseconds for an analysis. And I'm going to run this on 5 cores. And we can turn on mass scaling. Mass scaling allows us to make certain elements heavier, and that will increase the mass of certain elements, the smallest of elements. That increases the simulation speed so that we can accelerate this analysis even more. This obviously makes some components artificially heavy. If you're only talking about, a few tenths of a percentage, it's not a big deal, but if it becomes a large number, certainly it is cause for concern. So now we want to set up the boundaries and conditions and such. So because this is a symmetry model, I'm going to select the surfaces in the symmetry plane, like so, and constrain it so that it's not allowed to move in the x-axis. So that's a set of constraints. I want to make sure the clip doesn't move. So I can select a few surfaces here, for example. and put in a fixed support that makes sure the clip doesn't move. We can put a spring between the clip and this piece that pushes the bullet up, but instead I'm going to assign a force. So mostly because I'm not sure what the force is to push this up. I did an analysis and I think I ended up going with 500 newtons, which maybe too much. So it's going to be going in that direction. And we'll do 500 newtons, showing that it's pointed that way. Okay. One of the things that's interesting with Ls-Dyna is that we do take into account the thickness of the mid surface, and you can see this is the mid surface here. Sometimes we have to be careful with the mesh. The reason I refine my bullets is that if the mesh is too coarse, sometimes it'll be jagged and poke into my mid surface, and that'll cause simulation issues where things won't move properly. So I want to double check to make sure. For example, here it's pretty close. It's not quite touching. Hopefully it doesn't touch, but because this is a cylindrical surface, it's actually looks fine over here. But something we do need to worry about is whether this node, for example, is poking into or having any overlaps with my boundary. So one way of adjusting this is finding the mid surface, and we can choose to put it offset in the middle, bottom, or top. So if I change this, then the mid surface becomes the bottom of my surface, and that means the mesh goes on the other side. That gives us a little bit of room for the mesh to move. Okay. All right, so we want to pull the slide back. So I think what I did was I grabbed this piece here and I put in a fixed displacement or remote displacement. Remote displacement allows us to find the rotation as well, but in this case there's no real difference. I'm going to set everything to 0, and I can make a time dependent displacement. So from 0 to, let's say, 3 milliseconds. Right, the x is 0, y is 0, and z is 0. But I want to pull this back, so this will initially be at 0 and at 8 milliseconds. For example, I can pull this back to 70 millimeters. Change this to rigid here. At 1e to the -2, we're going to maintain, maybe hold it for 70, and then maybe at the end we push it back all the way to -20. So maybe not quite to the end. So we're going to pull this, wait a little bit, pull this, and then hold and push it back. So this allows them to model various mechanisms. This is an Excel spreadsheet, so we can easily copy and paste various types of displacement or pressure loads if you have those available. Okay. So it looks like there are a few other components where I place fixed support on, so I decided to select those surfaces and do a fixed support. Sometimes these barrels will start vibrating, and if you want to keep more of a rigid dynamics type of action, you can select surfaces here and constrain it to only move, for example, in the z-plane. That allows to avoid some vibration of the barrels. But if you're interested in the vibration of the barrels, that's totally acceptable as well. So that's the type of simulation we can set up. We're automatically tracking the total deformation for the simulation, and then we can look at things like deformation, stresses, strains, etc. And you can also extract contact pressure, shear forces, and all kinds of good information. So let's go ahead and run this analysis. So this simulation is predicted to take about an hour, but in reality it should only take a fraction of that because I'm running on 4 cores. Okay, so it's running nicely. Let's take a look at the results. You can see that maybe I put too much force in. This doesn't look like it's pulling back quite yet. Maybe this is the exaggerated results here. True scale. There you go. So we have the bullets kind of bouncing around as we push them up. It's about to get interesting here. You can see I was holding everything steady until 3 milliseconds, and then I think we start pushing it up. We start sliding the slide back. So instead of waiting for this to finish in a few more minutes, I'll show you the results of what the finished analysis looks like. So here is the deformation. Of the part as it goes up. You can see that I'm not a great firearms designer. The bullet is not going to the chamber as expected. I'm probably missing a few pieces of components that's necessary for that to happen. What's interesting here is we can plot, for example, the stress on individual components through this process. So you can look at how the stresses occur as the part is pushed in, and there may be some contacts that's happening unnecessarily here, and obviously the vibration is captured in this process. We can slow it down a little. Now, because contacts are automatically taken care of for explicit dynamics analysis, we don't have the standard convergence plots. Instead, we look at the kinetic energy buildup. So this is the energy of the system as it goes through the firing cycle. We can put in some sort of filtering at do some Butterworth filtering of the energy to look at what the plot looks like. We can export this and copy and paste this as needed. I also look at the internal energy buildup. So this is permanent deformation or internal strain that gets built up. Tells you how much deformation there is in the system as we go through the cycle. Finally, added mass. Now we can look at the overall mass of our system right now is about 0.65 kilograms, and we ended up adding 4 times 10 to the minus 4 kilograms, so maybe 1/1000th of the mass of the gun to this in order to speed up the simulation. So these analyses are extremely fast. I think this is on 4 cores. It only takes 11 minutes. If I have more computational resources, more cores, more HPC, I can certainly handle much larger models and run them very quickly to many milliseconds. But these type of simulation typically isn't practical for things that last on the order of more than a second. So that's the key limitation, and that is why we have a number of other methods for setting up these simulations. In addition to Ls-Dyna, we have static and transient structural, as well as rigid dynamics and Ansys motion to handle other types of longer duration motion events. So that's a quick overview of what happens when we simulate a bullet loading analysis in Ansys Ls-Dyna. You can see the vibration here. So that's not realistic, and that's probably because as I'm sliding this along, you can see the mesh is slightly bumpy, and that causes those vibrations. Lots of ways to simplify that: remove contacts from that area, smooth it out with a finer mesh, or set up displacement constraints so you don't have these jagged edges rubbing against the other parts. So a big part of setting up these simulations is using the right assumptions so we can set up analysis quickly. So that's a quick demonstration of how we go about modeling the motion of bullets as well as the firearm itself and how they interact. Hopefully this was of interest to you. If you have any questions, feel free to contact us at Ozen Engineering. Otherwise, like this video, subscribe, and I hope you have a good day. Bye-bye.